In 1989, an unusual physical phenomenon was observed, subsequently called sonar luminescence. The puzzling thing was that some liquids exposed to sonorous pressure became light emitters. Light is, after all, a form of energy, waves, or electromagnetic radiations. Many theories were put forward as to possible explanations for this phenomenon. Attention was focused chiefly on sonorous pressure exercised on liquids, but it soon became evident that at the heart of the phenomenon lay cavitation. What is cavitation? Gas bubbles implode when dissolved in liquids and subjected to enough pressure to jeopardize their internal equilibrium. The propeller blades of a floating craft present, in fact, a series of typical abrasions caused precisely by the implosion of such microbubbles close to the metal the blades are made of. The pressure exercised on the blade movement is sufficient to trigger the phenomenon. Even in such a minimum place and time, micropulsions concentrated an impressive quantity of energy. Ultrasounds caused, in particular, the collapse of bubbles dissolved into water at environment temperature and pressure. It was also puzzling that those bubbles exposed to ultrasonic pressure spontaneously turned a pressure wave into a shock wave. The time had come for measuring. When observing the quantity of light emitted in liquids stressed by ultrasounds, researchers began to estimate the temperature reached in microscopic spaces very close to tiny shock waves, revealing thousands, hundreds of thousands, and finally millions of degrees. These were obviously temperatures confined to infinitesimal spaces, sufficient, however, to oblige atoms dissolved into water to produce light, thanks to the release of the components they are made of. The idea that the bubbles could give rise to an endless series of very small shock waves, thus triggering a chain reaction, aroused immediate interest. It was, of course, necessary that the bubbles contain gases specifically useful for provoking nuclear reaction when exposed to cavitation. Researchers tried, not always successfully, different mixtures of deuterium and heavy water, mostly trusting to "let's see what happens if." During the analytic phase, a new word was created to identify this phenomenon: piezonuclear reactions. The first agencies to finance research in this new field of physics were the Ministry of Defense and the Ministry of Energy of the United States of America. The short but teeming volume by Professor Cardone, Towards Clean Nuclear Energy, the Discovery and Exploitation of Ultrasonic Nuclear Reactions, contains a synthetic summary of the developments produced by this research, ending as follows. In the experiments subsequently conducted by the Purdue University, Taleyakan finally decided to give up on external neutron impulses, to change liquid and go back to heavy water. Unfortunately, he was unable to do this without radiation for catalyzing bubble production. He mixed a base compound of uranyl nitrate, thus stirring up the customary sterile controversy, this time very violent, leading to the age-old result that in every dispute among scientists, the only loser is science itself. In fact, how can one possibly believe that nuclear energy can be produced with ultrasounds if, in any case, uranium is used? Moreover, the importance of the unknown factor pertaining to gamma rays still remained. It was uncertain whether they were produced or not, and if indeed they were, in what quantities. This was an ongoing, unsolved mystery, continuously hovering over all the experiments. In actual fact, these experiments left everybody with one question: whether pressure in the shape of a pressure wave or a shock wave or collapse by cavitation could or could not produce or catalyze nuclear reactions, and if it could, would they be new type or old? The Italian research. Our methods and approaches are different from the American methods, or even from last century German methods. Professor Cardone claims that we must think before acting, but without any preconceived beliefs or prejudices. We must be aware that the logic of nature is not like human logic, otherwise science would really be far too easy. Geometry. In theoretical studies around 2003, which preceded our experiments, it was largely debated in numerous universities: La Sapienza in Rome, Rome III, L'Aquila, Perugia, Messina, and Turin, and, obviously, at the CNR. Other universities also contributed to those preliminary studies, including the Universities of Danzig, Maryland, Harvard, Boston Polytechnic, MIT, and the European Laboratory of CERN. The initial idea was that the space surrounding the atomic nuclei is not as flat as a sheet of paper lying on a table, but that it is possible for nuclear forces to deform it microscopically, at least within certain limits. This hypothesis, briefly summarized in the mentioned volume, but far more accurately in Deformed Space-Time by Cardone, Mignani, and Springer, constituted the basis for an extremely complex theory. Both as regards how space and time was to be deformed by the action of surprisingly autonomous forces, such as radioactivity and nuclear reaction, and as to how an experimental machine able to monitor such deformation was to be created. This book specifically identifies those collaborators, events, and concepts which were to lead to the prototype that was finally constructed and put to work. Accurately specifies, furthermore, how and why scientists thought of iron as the ideal fuel to be used in the experiments. Iron is an inert, totally non-radioactive material. Bearing in mind the table of elements, every nucleus, starting from the smallest, deuterium, up to the biggest, uranium, is classified according to the increasing value of their binding energy per component. Halfway between the two extremes, deuterium and uranium, there is iron. Also has the highest binding energy value per component of all the elements' nuclei. Moreover, iron is inert, therefore non-radioactive. Because it has the highest binding energy, iron is less advantageous for nuclear energy production and is less inclined to do so. Jokingly, we might say that the iron nucleus is as hard as iron. Therefore, when taking account of the elements, iron should be considered the least suitable, according to common sense, as Fermi would have said. All the foregoing, however, occurs in normal conditions, i.e., in a flat space. Vice versa, in a location deformed by nuclear energies, iron presents advantages. In fact, if an energy threshold higher than all binding energies is to be reached, the nucleus with the highest energy is the nearest one that, with equal power provided, reaches that threshold before other nuclei, and, most important, in the shortest time. With this very simple and elegant reasoning, Perconti sums up other, extremely complex reasonings and calculations. The experience. The project was implemented by a team of experts led by Professor Cardone, achieving a highly efficient synergy between the academicians and the Italian army. Of course, demanding that iron emit nuclear energy within the space of 10 minutes seemed to be a very tall order, and with ultrasounds to boot. To understand the hugeness of the event, we have to consider that ultrasounds affect atoms 100,000 times larger than their nuclei, and that the nuclei possess energy 100,000 times greater than the atoms, hence the enormous disparity between nuclear and chemical energies. The idea was, however, that in the deformed space, in the presence, therefore, of a deformed geometry, it would be possible to transform a tragically unfavorable lever into a favorable one. Tested and constructed by the Army, the cavitator, the name of the equipment, presented two strong points in comparison with previous experiments conducted in America and Perugia: the separation of the sonotrode from the reaction chamber and a new concept as regards the cooling system. Leaving out the details, the proportions of the sonotrode and the reaction chamber had to correspond to extremely precise geometry due to the thermal expansion to be undergone. The extreme attention paid to these two aspects, geometry and the cooling system, would allow the machine to work at full capacity with no time limit. The machine worked. Ultrasound emissions were 20 kilohertz, 20,000 oscillations per second, with 100-watt intensity. Now, the problem to solve was the choice of fuel. Various elements were chosen, according to mass and nucleus energy per nucleus component, for example, lithium, aluminium, iron, chemical elements. These three in chloride form with added iron nitrate. Obviously, nobody expected any neutron emissions from the lithium and aluminium, but from iron they did. Quantity, proportions, dosage, and whatever else was needed for the success of the experiment was, however, provided for by theory. Now, another fundamental component was needed for the verifications, an impeccable neutron detector. We opted for the best, the Canadian BTI thermodynamic detectors. These detectors made it possible to block, make visible, count and photograph the bubbles of one hydrocarbon dipped into jelly and brought to the boil by neutron energy. The costs were courageously borne by the Army. Despite the remarkable reliability of the verification detectors, in 2005 the system was equipped with another detector system, photographic plates made of polycarbonate, Cr39, corrected with boron. Finally, in 2006, a trifluorine boron detector was added for electronic data recording. All the foregoing aimed at making possible, within the 90 minutes of the machine's operating cycle, a graphic illustration of the neutron emissions, their quantity, and the amount of energy produced. Switch on. During the 90 minutes of the experiment, no neutron emission was measured as regards lithium and aluminium. But we were speechless when we observed iron. First experiment, first success. The cross-checking of our three detectors, after about 50 minutes, began to emit, in perfect harmony, signals indicating nuclear activity, neutron emission. No presence of alpha and beta radiations was revealed outside the reaction chamber, not even during the 90 minutes of the experiment, nor after the conclusion of the experiment and the switch-off of the machine. There were no gamma radiations whatever, in any type of condition. Further comparisons were made using iron chloride and iron nitrate, but the results were the same. The chemical form did not influence the production of neutrons. Only the presence of iron was decisive. An increase in the quantity of iron inserted into the reaction chamber, corresponding increase in the time needed for neutron production. This definitely confirmed a state of inertia, and therefore a waiting field during the process of the production of the piezonuclear reactions mediated by ultrasound and cavitation. In 2006, experimentation was moved from an Italian army location to CNR laboratories in Rome in order to check the repeatability of the phenomena. The results were the same. The absence of alpha and beta radiations was identical. The absence of gamma radiations, verified by us, became a field of investigation also for other researchers. Accurate experiments using spectrometers with sodium iodide crystal and thallium further confirmed the absence of gamma radiations. At this point, after having supervised the results, the director of CNR suggested a very interesting check, i.e. a comparison between our ultrasound machine and a conventional uranium-based nuclear reactor belonging to the Rome Casaccia Enea Center. Once again, this produced a surprising result. Double the energy deriving from 30 kilograms of uranium was produced by CNR's experimental machine using just a few grams of iron chloride. Another surprise. But what would be the behavior of an element which, unlike iron, is radioactive? Something surprising, even though already predicted by theory, happened with thorium. Solutions with very low thorium-228 content were prepared. This was made up of 90 protons and 138 neutrons, which, it must be borne in mind, is an aza-alpha emitter, emitting 6 alpha particles and forming, on polycarbonate photographic plates, an image resembling the fingers of an open hand. Its radiation is therefore unmistakable, even in the presence of other environmental radiations. The natural time in which its radiation and contents are halved amounts to roughly 2 years. Of the 12 samples prepared, 8 were subjected to cavitation in our machine, and the other 4 used for comparison. At the end of the experiment, the cavitated samples were subjected to analysis with a high-resolution mass spectrometer, quadrupolar with magnetic sector. The result was that both content and radioactivity had been precisely halved. The neutron measurement did not produce good results. What were we to think? We believed that the thorium, when subjected to cavitation, had changed 10,000 times faster than its normal speed, that it had been subjected to piezonuclear reactions, which had modified its nature, causing it to exceed the energy threshold of radioactive force, beyond which even the geometry of that force was no longer flat. The iron and thorium examples could become emblematic of something different, that going beyond the deformation threshold is a little like passing through Alice in Wonderland's mirror, to reach a place where inert iron emits neutrons, even though it is the most handicapped element, whereas radioactive thorium loses its radioactivity in a very short time, producing inertia. The prospects are multiple and way beyond the imagination. Just imagine the possibility of neutralizing present radioactive waste produced by conventional atomic power plants, not to mention the quantity of energy obtained from iron, far more abundant in nature than oil, and even more so when compared to uranium. Professor Cardone inserted in his slim but awesome volume a series of important observations pertaining to the exploitation of the foregoing phenomena, together with an in-depth analysis of the contemporary geopolitical and economic scenario. We seem to be contemplating an abyss through a mere crack. The scientific discoveries linked to piezonuclear reactions are so numerous and amazing that they furnish more than one clue to the possibility of redesigning part of theoretical physics, as Dr. Petrucci sums up. Phenomena have been pinpointed which have revealed a new type of physics. Physics wherein the time-space factor may be deformed and participate in natural phenomena, not only as a simple, flat and rigid stage where the phenomena occur, but in itself an integrating part of such phenomena. Energy, space and time, three different aspects of one sole entity. A revolution? Perhaps. These experiments, conducted with reduced means and staff, have in any case produced, over a very short time, starting points for previously unthinkable investigation in the fields of chemistry and physics. The foregoing primary, summary findings represent the hope that appropriate resources may urgently be invested in order to make concrete further promising research for the universal good of the entire world.